Yeah, so thank you for the introduction. So we already heard a lot of in the term of energy production. So now we go the other side. We go on the consumer side and go on energy consumption management in industrial production. So the new base standard for the topic of energy. So I will do this presentation together with Wolfgang Mahnke, as already announced. And so what we would like to show you today is first to have some topics about the motivation for energy management, then go a little bit deeper in how energy management works, which are components for energy management in industrial production. Then I will hand over to Wolfgang, who does the presentation of the information model out of the companion specification. And at the end, we will close with a short summary. So what are topics for motivation for energy management? We heard a lot, but at least I will start with some words from my children. So if I ask them for motivation for energy management, of course, they will tell me the goal is to lower energy consumption, to cut down product carbon footprint, and to save the world. Of course, if I ask my financial officer, he will tell me the goal is to reduce energy costs. And you still know if you go to buy a new dishwasher or washing machine, you will see all these energy labels. And of course, these energy labels and the ranking on the energy labels is a good criteria or important criteria if you buy this machine or not. And then we also know such labels which are good for your image. So you buy, for example, foods if there's an eco label on it. But also a quite important topic, which is not in the main focus up to now, is balancing of energy. So with today green energy, we have the problem that storing of energy is quite expensive. So if we want to be much efficient and cut down energy cost, it's quite obvious that it's necessary to have a good management between energy producer and energy consumers. So, and for this we need information models and standardized interfaces. So, but first have a look on application areas for energy management. So energy saving in industrial production is just a long-range term, and so the goal, of course, is primarily to cut down the costs for energy. And so if such a project starts, first task to do is a consumption analysis, so have awareness and measure energy flows in your production. And out of this, define saving potential, so measurements to save costs. And for this, you have two possibilities. So, of course, reduce the overall power consumption, but also the possibility to consume your power at the right time. So, for example, to avoid peak loads, and with this to avoid penalty payings, high penalty payings for peak powers, or to compensate for reactive powers, and so far. So, but let's go further with reduced energy consumption in production. So there you have the possibility to save energy in production, in operation. So of course, this can be done by introducing a new technological process which consumes less energy, or use energy efficient components like energy efficient drives, or optimize dynamic systems. But there's another possibility, which is also quite good. It's to save energy in pauses. So we have a lot of industry which is not continuous but intermittent. For example, body shops and car factories. And there a lot of the equipment is only temporarily used, and if they are not used, the goal is to drive them in an energy optimized standby state. So the red arrows show which measurements or which functionality is in the power consumption management companion specification and addresses these tasks here. And also be aware that increasing of energy efficiency is a continuous process. So it's not done once and then it's okay. It's a continuous process. So you analyze your energy consumption, you define new energy savings, you realize them, then again analyze and so far. And you see to two of these steps, of these three steps, the energy consumption management companion specification contributes. But now let's have a look what's in the companion specification, what's in OPCOA part 34-100. So there are mainly two functional clusters. So the first one is power metering and monitoring. So of course we measure energy related measurement values like power consumption or a total energy odometer. But there are also other relevant measurement values which address power quality, for example, a measurement of idle power or of harmonics. So to cut down energy losses in power distribution. So use cases for this is energy metering, of course, then evaluation for energy cuts and saving potential. But another quite important topic is predictive maintenance. So at least your energy consumption, energy footprint monitored over time gives a good indicator if your process is running correctly, if machines or devices need maintenance. The other cluster in the companion specification is power standby management. There we distinguish between two possibilities. So a complete power down, switch off of the device with reactivation over switch on, wake on, LAN, or the device is still on power and manages its internal standby state. So that's standby pause management. So with this, we have use cases where we can save energy in intended pauses, for example, breakfast pause or shift changes, but also in unplanned pauses. So for example, if there's a machine breakdown in a production line and all the other machines have to be stopped for a specific time for the repair. But before I go deeper in the standby management, technology of standby management, I would like to give a short overview about the setup of the working group. So it's a joint working group between different partners. So one is a PI organization, Profibus Profinet organization, who introduced the Profi Energy profile in 2012. And then some years ago created the OPCOA part 30-141, the Profi Energy companion specification. So that's contribution to this standard. Then the other partner is ODVA with its ZIP energy technology, who contributed mainly also energy resources which are not electric. Then we get also support from universities, Hochschule Hannover and Helmut Schmidt University, with a public funded research project where they created an unified energy management information model. So this is mainly used for the measurement values. And of course, the VDMA, who hosted this project, this working group in its machinery program, and Heiko Herden was the lead of this project. So what's new now? What's the main contribution from OPCOA part 34-100? That's to have a now harmonized information model for the IT world. So now it's possible to map all the different energy-related variables from the OT area, from production cells running different field bus systems, and also different energy management profiles in a harmonized way to the IT world in a harmonized OPCOA model. So now let's have a short look on what's standby management and how this works. So standby management was the very early functionality of energy management in industrial production. So it started in 2009 together or because of the financial crisis. So automotive industry, they found that if still there's nothing produced or less production, there's higher power consumption. And so it was obvious that a standby management it needed to have a more efficient usage of energy. And this was when Profi Energy was introduced in 2012. So this figure shows the standby management basic model. So standby management takes place, energy saving in standby management takes place in a pause situation. So the machine or device is not in operation. So it's in pause, which is here addressed by state ready to operate. And then the device offers one to multiple of these energy saving modes. And so they differ in the power consumption, and typically if an energy saving mode has less power consumption, which means saves more energy, he needs more time for the switching in the energy saving mode or back to ready to operate. So therefore typically low energy saving modes with high switching times are used in long pause situations, while high energy saving modes with short switching times, they are used for short pause situations. And another important feature of the standby management is the definition and the attributes for the standby mode. So in this figure, you see how a device moves from ready to operate in an energy saving mode and back. And here you see all these attributes related to the standby mode. And you see here only energy variables, power variables, and time variables are used. And therefore, the energy saving mode fits to every device, to every machine, and to every application process. So far to some theory of energy management. So now let's go further to the companion spec and the information model. And for this, I would like to hand over to Wolfgang.
All right, so welcome to the information model part of the energy consumption management. It's mainly split into three areas. One is the energy consumption measurement in order to monitor the energy consumption. Then we have the standby management to save energy, and also the sleep mode wake on LAN functionality in order to save energy. The energy consumption measurement is done in a way that we do represent points in a system to measure potentially several energy data. Therefore, we have defined an object type called energy measurement type. It contains an application tag to uniquely identify the functionality. This application tag can be set by the end user or the system integrator. And then it has one or more variables representing individual measurements. Those variables have, we defined a specific variable type for that, providing additional metadata like the accuracy of the measurement, the engineering unit, of course, and other things. We will look into this in the next slides. And in addition, we do have the possibility, if the energy measurements are aggregated over time, that we are resetting those and start the measurements from the beginning. Therefore, we're using some base infrastructure from the industrial automation specification. So let's take a look into an example first. We have here a system where we have two measurement points. One is a power meter and the other one is for air extraction. The power meter is measuring three different aspects. One is the active power, and then we have the active energy consumed and the active energy generated. The air extraction is measuring completely different things. It measures the pressure, the volume flow rate, the volume, the temperature. So you can see we do not only deal with electrical energy, we deal with all kind of energy. The different things you can measure, for those we have defined, we standardized those. We have defined specific measurement IDs. So you can see here on that slide a small excerpt of some of them, including the pressure, temperature, volume, and so on. In general, those measurement IDs are defined in a comma-separate value file. We have over 250 standardized measurements already defined in the first version of the specification. They all have, of course, a unique ID, and then they have a predefined name, a predefined description, and engineering unit. We also define the measurement period and, of course, which data type to be used. Having over 250 different of them is on the other hand, of course, also challenging. So which one should I provide? For the most common use cases, we have defined a few interfaces providing a set or defining a set of measurements that you're supposed to provide. Those interfaces are based on Profi energy profiles. Might be that we add more of those in the future, but and they are all on electrical energy, and that helps you in picking what of those are actually supposed to be supported. And they can, of course, be deployed on the instance directly or on a type, depending on how you're doing your model. The accuracy of the measurements is the information about the accuracy, how the measurement is done, is provided by, first of all, having accuracy domains, and then each accuracy domain has a set of accuracy classes. So there are different ways to expose the accuracy. Each measurement is referencing to which mechanism, so which domain is used, and then, of course, the concrete accuracy class in that accuracy domain. We have defined 4 different accuracy domains. The server represents in its address space the accuracy domains it's supporting. Potentially you can also add additional ones. We hope that the one we have defined are good enough for your applications, for your use cases. And you, of course, only have to provide those which you're actually supporting in your server. And as I mentioned, all the measurements are pointing to what accuracy domain they're referencing to, and then providing the concrete accuracy class in the context of that accuracy domain. So this is about the energy consumption measurement. The standby management, Andreas already talked about that. So we have a high-level state machine. You can see here on the left hand. We're not representing the whole state machine with all its bloody details in the address space. So we discussed this and said that's not necessary. But we have an energy standby management type, and it provides the high-level state as kind of an enumeration. And then, as you have learned, we have those different energy saving modes, and they are also provided here in what concrete energy saving mode you're in, and of course also providing the metadata, what are the supported modes in order for you to interpret the data or provide the data in a reasonable way. And in addition, we do provide control methods to switch the energy saving mode or go in or go out of the energy saving mode. And then we have the wake on LAN functionality. We have an additional object type for that, and this provides a bunch of metadata for this wake on LAN functionality, plus a control method to control that functionality. To summarize all that, we have the energy consumption management companion specification out as a release candidate, and it will become a release very soon. The content is, of course, we have the energy consumption measurements, not just electrical energy. We have standardized over 250 different measurement IDs. Of course, you can also add, if you have some, let's say, more uncommon measurements, you can use them in the context of the specification as well. We have 5 profiles for common usage of energy measurements. The energy saving can be done by the standby management and the sleep mode wake on LAN functionality. This specification hopefully soon becomes a release. In addition to that specification, we're currently working in the machinery working group on integrating that into the machinery specification, so that you have a common way if you want to represent those energy measurement information functionality in a machine or a component of a machine, how to do it in the best way, and from a client perspective, be capable to find that information. So that's all I wanted to say about the energy consumption management information model. Thanks for listening, and if you're interested in more information, just download the specification and there are all the bloody details.